right, students, welcome to Unit 6, baby. Things are going to start cranking up a little bit. We are starting off with our brand new packet here, our Unit 6 packet, which is a little thicker than the previous one. So we're going to start getting into the good stuff of chemistry here. Things are getting a little more serious. Before I get you guys to start on your notes, let's do a couple of things to review. So just a reminder, when your protons equal your number of electrons in an atom, that means your charge is neutral because those positive and negative charges are canceling out, okay? And valence electrons are electrons in the highest energy level. They're the only ones used in bonding. So, for example, this atom right here, okay, so let's say it's positively charged nucleus is here. It would have 3 valence electrons, okay? So we got this guy right here, this guy, and this guy because they're the ones in the highest energy level. If this guy were to move down here, it would only have 2 valence electrons. Now it only has 1 valence electron. But if this guy were to move right here, okay, we'd still be talking about 3 valence electrons once again because it's how many electrons are in the outermost ring that's occupied, okay? So this ring on the outside right here, that guy wouldn't really be there if there weren't any electrons in it. But if we go back to our original one, boom, right here, this has 3 valence electrons. But this is also 3 valence electrons because it's all about how many electrons are in the outermost occupied ring, okay? And so these are the electrons that are going to be used in bonding and pretty much any reaction that this atom is going to take part in, okay? So let's go ahead and get cooking. You'll definitely want this periodic table out, okay? We're going to put some more labels on here. So you probably have things like metals give away electrons and become cations, and nonmetals take electrons and become anions, and 1 valence electron, 2 valence electron, 3, 4, all the way up to 8 in group 8, all that good stuff. So you'll need this periodic table. We're going to come back to this here shortly to label it a little bit more. Okay, so let's talk about chemical bond notes. So atoms join together chemically to become stable. To become stable. It is all about this word today, right here, right here. Stable, stable. All chemistry, in a way, is centered around the idea of what is the most stable thing for the atoms involved to do. Okay, a sodium does what it does because it becomes more stable when it reacts the way that it does. Okay, and so any element on a periodic table, it will always look out for itself. It will always do what is the most stable thing for it to do, so to speak. And so here's where valence electrons come into play. They're transferred, which means they are either given away or taken by an atom. So some atoms are giving away electrons, other atoms are taking electrons, but they're going to be transferred in some way. And the only reason why electrons are going to be transferred is so that elements become more stable. Okay, if an element doesn't become more stable by giving or taking away electrons, it won't do it. And sometimes electrons can be shared to become a new chemical. So we'll talk about this idea of sharing a little bit more later in this unit. So at first, we're going to focus on electrons being given or taken, but just an FYI, they can also be kind of shared in a mutual agreement between atoms. We'll get to that more later on, though. And again, only valence electrons are used in bonding. So those electrons on the outside ring, those are the only ones that are used in bonding. So the number of valence electrons is valence electrons in the highest energy level right there. Now let's talk about the number of valence electrons at a couple of different elements here. So we have sodium and fluorine. Now this atom on the left, sodium, grand total number of positive charges is 11 because it has 11 protons. And currently the overall electrons is 11 as well. Okay, starting off as a neutral atom, sodium has 11, and starting off as a neutral atom, will have a charge of 0. Fluorine, element number 9, has 9 protons and 9 electrons respectively, giving it a charge of 0. Because remember, we take protons minus electrons to find our charge. And this brings us to the driving force that sort of dictates how an atom will become stable, the octet rule. So you think of like an octopus or an octagon. Oct means 8. So this is the rule of 8. So atoms will gain or lose valence electrons to obtain a full outer level of 8 electrons. So all atoms are trying to get 8 valence electrons in their outermost occupied ring. 8 valence electrons in the outermost occupied ring. Now, there are 2 exceptions to this rule. It's going to be your 1s elements. So, for example, hydrogen and helium, they're in that first period of the periodic table, the 1s. My camera tilted a little bit there. And so those 2 only want 2 valence electrons. There are a couple other exceptions to that rule, but it's mostly just that 1s, that top row there in the periodic table. And so atoms are stable when they have full outer levels, which means 8 valence electrons, okay? So once you get 8 valence electrons, that outer ring is considered full, and it's that being full that causes the atom to be really stable, okay? So having a full outer ring causes an atom to be nice and stable. So if we take a look at these different electron configurations, so we have sodium, magnesium, fluorine, and oxygen, and notice I put neutral charges next to all of them. Right now, do a quick pause, write out the full electron configurations for these 4 elements. That should take you a minute or 2, and then we're going to go ahead and continue. So hit pause right now to do that. All right, so now that you've paused, here are the configurations that you should have gotten. So sodium, fluorine, magnesium, and oxygen. Now, sodium and fluorine, again, these are the pictures of the 2 elements we have up here. Here's what's going to happen. You'll notice that sodium has 1 valence electron. It's this last one in the 3s1, so there's only 1 electron in that 3rd energy level. And if you come up here, you'll notice here's that 1 electron in that 3rd ring around sodium, okay? Fluorine has 7 valence electrons. You can see that's in group 7, but you can also see, like, okay, its highest energy level is 2. There are 2 in the 2s, and there's an additional 5 in the 2p. And so fluorine has 7 valence electrons. So it would be these guys around the 2nd ring right here. Now, here's what's going to happen. Sodium wants 8 valence electrons. Fluorine wants 8 valence electrons. Sodium is really far from that because it only has 1 valence electron. Fluorine is so close because it has 7. So here's what they're going to do. They're going to form a deal where this 1 valence electron from sodium is actually going to leave it, and it's going to hop over here into this ring right here for fluorine. So from fluorine's perspective, fluorine now has 8 valence electrons. It gained 1. And now instead of having 9 electrons total, it has 10. And if it has 10 electrons total, instead of having a charge of 0, it's actually got a charge of 1. Sodium, from its perspective, okay, so once this electron leaves, so if I kind of erase this guy right here, okay, it's over here now. On the right, I'll draw it in fluorine. There we go. There's that new electron. Okay. Now, if you look at sodium, it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Okay, remember, valence is defined by the outermost occupied ring. And now that there are no longer electrons in the 3rd ring, the 2nd ring becomes its outermost energy level. And so sodium also now has 8 valence electrons. It had to get there by losing 1 electron. So instead of 11 minus 11, we have 11 minus 10 now. And so the charge of sodium, when it is stable, is +1. Okay. So these are what we would call stable charges. So sodium is most stable and it has 8 valence electrons. It gets those 8 by losing 1 electron. And so its stable charge is +1, whereas fluorine's stable charge is -1. And so you can kind of see why metals tend to form cations, because they usually only have 1 or 2 or maybe 3 valence electrons. It's easier to get rid of those than to gain a bunch to get to 8. And you can also see why nonmetals tend to become anions. So like fluorine, for example, if it just gains 1 more electron, it's going to get its full outer level of 8 valence electrons. And so it's more advantageous to gain than to lose in that situation. So another way to sort of see this with your electron configuration, if you have 1s2, 2s2, 2p6, 3s1, this 1 valence electron right here is actually going to hop in the 2p of fluorine. And so really fluorine will have this configuration as well. So if you change their charges to indicate this transfer of electrons, sodium with a +1 charge has an electron configuration of 1s2, 2s2, 2p6, and fluorine with a -1 charge has an electron configuration of 1s2, 2s2, 2p6. Okay, so these two elements actually have identical electron configurations when they're stable. Over here with magnesium and oxygen, so magnesium has 2 valence electrons, oxygen has 6, and so these guys are a pretty perfect marriage as well. These two are going to hop over here. So now they're going to jump in at 2p, and so really, if I write this a little cleaner, more cleanly, so we have 2p6 down here as well, because it was 2p4, but it gained a couple of electrons. And so no longer is this magnesium with a neutral charge. This is magnesium plus 2 because it lost 2 electrons. And this is oxygen minus 2 because it gained 2 electrons. Okay? And so we want to go ahead and write all these stable charges on our periodic table. So if we go back to this periodic table, so here we are. We got the number of valence electrons. You should put the most stable charge above them as well, because if all of the alkali metals have 1 valence electron, that means they're all likely going to give away that 1 valence electron to become more stable. And so elements in the first period, the alkali metals tend to have a charge of +1. As we just saw with magnesium and anyone else with 2 valence electrons, their more stable charge is going to be +2. Boron and Co. with their 3 valence electrons will be +3. Now, those in the middle, carbon could gain 4, it could lose 4. So it could go either way. It's not really easier one way or the other because it's sort of in the middle. So we put plus or minus 4. So elements in carbon's group, they could be either way. Once you get to nitrogen, it has 5 valence electrons. It's closer to having the full 8. So it's going to be easier for that group to gain rather than lose. So to get to its full 8, it's going to need to gain 3 electrons, giving it a charge of -3. -2 for oxygen and Co. -1 for the halogens. And check this out. The noble gases, here's why they don't react with other elements. They already have 8 valence electrons. They are already stable. They already have no interest in becoming more stable. Okay, it's not really a thing for them. So they won't gain or lose electrons like ever. And so their stable charge is actually just 0. It's neutral. And you'll also notice, so electron configurations for noble gases, they always end in P6, with the exception of helium is that goofy part. But you'll also notice that other elements, when they become stable, like your 4 elements down here, they all ended up with a noble gas configuration. Look, 1s2, 2s2, 2p6. For a neutral atom, that's for neon, but that could also be a stable +1 sodium. Or it could be a stable +2 magnesium. Or it could be a stable -2 oxygen. You'll notice that elements really want those electron configurations that line up with the noble gases because those are stable electron configurations. And so we can kind of see, like last unit, you guys learned some of the trends. Oh, metals, cations, nonmetals, anions. The noble gases are unreactive for some reason, whereas the alkali metals are super reactive. This is part of the reason why that is. It's all about stability. It's all about stability, getting those 8 valence electrons. So really sending this home, the bottom line, when the octet is full, the atom is stable. It's all about stability. So full means 8 valence electrons for most atoms, 2 valence electrons for your weirdos like hydrogen, helium, and we'll talk more about them as the unit goes on. But it's called the octet rule for a reason. It means that most atoms want those 8 valence electrons. Not literally all, but almost all. Okay? And so that brings us to this worksheet right here, the chemical bonds worksheet number 1. So I want you guys to go ahead and get cooking on this. Now, you will find the answer key to this worksheet this way, right below this video, okay, in your Monday folder here on Schoology. So you can kind of do a couple, check a couple. So we talk about why bonds form, electron configurations, stability, all this stuff. Are any of these elements stable already and why? Okay, so think about which elements in here should already be stable without any transferring. I want to go ahead and take a look at a couple of problems on the back before I let you guys go. So this is on the back of your chemical bonds worksheet number 1. So draw what will happen with the valence electrons for the following elements. So I'm going to go ahead and let's look at the potassium and iodine one. So potassium, element 19, it's an alkali metal. It has 1 valence electron. Iodine, element 53, it has 7 valence electrons. So just to give a simple drawing, I put a K for potassium. I drew 1 electron around it. An I for iodine, I drew 7 electrons around it, okay? So what is going to happen? This question is asking me, draw what will happen with the valence electrons when the following elements react. Then tell what the charge of the element is once the electrons are transferred. So here's what's going to happen. This element right here, or I'm sorry, this atom right here is going to send its 1 valence electron. So this electron is going to go there, okay? And so you can kind of draw it with the arrow like this, or if you want to just go ahead and get up, I'm just going to grab this guy, toss it over here. So now potassium has 8 valence electrons, iodine has 8 valence electrons, and I need to indicate their charges, so I'm going to go ahead and write a big old +1 above potassium and a -1 around iodine. Now some of these get a little trickier though, so lithium and oxygen. So if we take a look here, let me get my oxygen a little more centered. Uh-oh, come here you. There we go, okay. Oxygen's got 6 valence electrons. Lithium's got its 1. So in this situation, here's what we can do. So this 1 valence electron here is going to hop on over to oxygen. Boom. Okay. And so lithium loses its 1 valence electron. It's happy now. Lithium has 8 valence electrons. We're good, or a full outer shell. It's good to go. But if you'll notice, oxygen still only has 7 valence electrons. So this isn't a good deal for oxygen. Oxygen needs those 8 to become full. So it works for lithium, but it doesn't work for oxygen. And if it only works for one of the 2 elements involved, it's not going to happen. So this reaction wouldn't occur in nature with just 1 lithium and just 1 oxygen. So here's what needs to happen. A second lithium needs to come into play, okay? And so this second lithium, which can also become happy by transferring its 1 valence electron, will do so. And now oxygen is happy. So all parties have to be happy. It's kind of like a marriage, okay? 2 people aren't going to get married unless they both want to get married, unless it's good for both of them, not just one of them. So now oxygen's got 8 valence electrons, and the lithiums both have full outer shells. And so when we look at this, the lithium will become a +1 charge, but the oxygen will become a -2 charge because it needed 2 electrons to become stable. And so you can also see that for lithium and oxygen to form a bond, you need 2 lithiums for the 1 oxygen. And we're going to talk about this a lot down the road. But please note, 2 lithiums to the 1 oxygen. So that should be plenty for you guys to get cooking for today. Please email me if you have any questions. So I know I'm out of school today, but I will be checking my email. So if you have any questions, need help with anything, please let me know. The PSAT is tomorrow, by the way. You guys will have another recording in your Tuesday folder for PSAT day since people won't be coming into school to learn. And then, yeah, that should be that. All right, you nerds. Make sure you answer your lecture questions right now. Go get your 6 points for your 3 lecture questions. And that should be that. Have a good rest of your Monday and come to this Tuesday, to the Tuesday folder on Schoology tomorrow. See ya.